Hello, can you please confirm that you can see and hear me, see the presentation and hear me?
Yes,
Okay, thank you. Okay, so we are in the last phase of our course after the Deepavali vacation. So I would just briefly like to return to a few points we took up when we ended the last class. One was the Biot-Savart law, using which, I'm not going back to all the details of the law, but using the Biot-Savart law, we were able to find the magnetic field due to a current passing through a long straight wire, an infinitely long wire for preference. So use, sorry, just a minute, please. Yes. And so what we found that the magnetic field of such a wire will be given by this formula, mu naught by 2 pi into I by S. I being the current passing through the wire and S is the radial distance on a plane that is with respect to which the wire is perpendicular. So the wire is like an axis. So if you treat that axis to be the axis of a cylinder, and if the cylinder has a radius S, then the magnetic field strength will be given by the formula mu naught I by 2 pi S phi cap. So the magnitude of this magnetic field depends on the S coordinate, but the direction of this magnetic field depends on the is along the phi cap unit vector. And we also found that the divergence of B, the divergence of this magnetic field, is zero, which is one of the Maxwell equations. I haven't given you a formal proof of this equation. We have just used an example, a simple example actually, of a current that is passing through an infinitely long straight wire. And but this principle, this equation, divergence of B is equal to zero, will hold true in all respects. So that is generally true. And then we ended our discussion in the last class, discussing that if the divergence of a magnetic field is zero, then its closed surface flux will also be zero, which is something that has got important consequences in various cases. When we ended the last lecture, we touched upon a few of those cases. Like one of them I do remember was the case of sunspots. Okay, so now what we shall do is to move forward and apply and try to find out Ampere's law. Let us see what is it like. Um, so remember, the Maxwell equations, what we have found, one you already know, one is divergence of E is equal to rho by epsilon naught. That is also Gauss's law in differential form. Divergence of E is equal to rho by epsilon naught. You have gone through several tutorial problems and an examination question, all those things. So the second thing that we are doing, have now is divergence of B is equal to zero. Like I told you earlier, that the Maxwell equations are simply the divergences and the curls of two vector fields, namely the electric field and the magnetic field. So we have looked at the case of the divergences, both for the electric as well as for the magnetic field. Now we shall gradually move forward and look at the curl properties. And in so doing, we shall first have to look at Ampere's law. Let us see now. First, let us discuss this diagram over here. Try to understand the meaning of this diagram. I have drawn a green circle, as you can see. This is a green circle with a black border also. This is the cross section of a wire. Let us say a copper wire. A copper wire is thin, but if you look at it up close, it has got a cylindrical structure, a cylindrical cross section. So if you cut a copper wire, the exposed face will be like a cylindrical disc. So this wire is pointing straight at you. Ideally, the wire is elongated, but if you turn the wire and look right down the wire, you will just see the circular end cross section of the wire. If the wire is thin enough, it will actually look to you like a point-like structure, but under a microscope or whatever magnifying glass, you will see a circular cross section. Maybe a thicker wire with a circular cross section will serve the purpose better. So this cross section, across this cross section, current is passing. These black dots are the current lines. So a wire is like a thin line, although it's got a cylindrical, circular cross section. Through the wire, current is passing. Okay, so if you track the current like a straight line, and then if you look down the cross-sectional face of the wire, the current lines will look like black dots. Just think of a line. If you turn the line around and look straight down the line, as if the line is pointing towards your eyes, then the line would look like a black dot. The end point of a line is a dot. So these dots are actually lines, but they are coming out of the plane of the paper and going towards you. So basically, you are just looking down the barrel, looking down a wire, cross-sectional wire. So there are several such black dots. A whole lot of current lines are passing through this wire and traveling towards your eyes. Now, if you use the right-hand rule, what does it say? That if you take your right hand, stick your thumb, and make your thumb point in the direction of the current, then the fingers curled around will give you the direction of the magnetic field. So this is like this. So here you take your right hand, stick up the thumb, and then make the thumb point towards your eye. So the thumb will be pointing towards your eye and your fingers will be curling round like this in an anti-clockwise direction. So that will be the direction of the magnetic field. Now comes something important. Like in the Gauss problems, you have worked with an imaginary surface known as the Gaussian loop. Gaussian loop is an imaginary surface that encloses all charges. And so it is that here you are drawing not a surface, but a closed one-dimensional loop, a circle, a rim of a circle, a hoop. So this is an imaginary Amperian loop that you have drawn, and these imaginary Amperian loops coincide themselves with the magnetic field that is generated by the current passing through the wire. Okay. Now let us see what we can do with this thing. A little line element on the Amperian loop is given by dl, and dl is going in this direction. So in general, in cylindrical coordinates, dl is written as dss cap plus sd phi cap plus dz z cap. Okay, fine. And what about the magnetic field itself? So if this is the current is going towards you. This is the radius of an imaginary circle around the current. Then the magnetic field at a radial point S, radial position S. This is a cylindrical symmetry. You just expect that you're looking straight down the cylinder along the top surface. So the magnetic field will be mu naught I by 2 pi into 1 upon S phi cap. So the magnetic field is going round and round this way. And you have also coincided the magnetic field with an imaginary loop known as the Amperian loop. Just like you have a Gaussian surface, so it is that you have an Amperian loop. We shall discuss the significance of the Amperian loop soon. So what I would now like you to do is to find the line integral of the magnetic field around the entire circumference of these dotted circles. The line element is dl. The magnetic field is mu naught I by 2 pi s phi cap. So the magnetic field is going this way. The direction of the magnetic field is circular, whereas the strength of the magnetic field changes along the radius, right? So the direction is tangential to the this circle, whereas the strength of the magnetic field varies along the radius of these circles. Okay. Now B dot dl, if you have to integrate the magnetic field all around the loop, you have to write B dot dl, closed path integral. Fine. So what is it like? Let us see now. Mu naught I by 2 pi s into dot dl. Now this thing has got phi cap. So phi cap dot s cap will be 0. Similarly, phi cap dot z cap will also be 0. You don't have to worry about what else is there. That is no account. So the only thing that survives is phi cap dot phi cap. Only this second term survives. When you take the dot product of B and DL, only the second term makes a contribution. The other two terms will cause zero dot product, scalar product. So basically, you just have to write mu naught I 2 pi by 2 pi s phi cap dot s d phi phi cap, and phi cap dot phi cap will be 1. So you just have 1 by s into s d phi. This s d phi comes here, and this s and this s, this and this. These two will cancel. Mu naught into I. I is a constant current. It's a steady current. We have discussed the meaning of a steady current, that at any position of observation, the current will not change its value in time. So that is a steady current. So mu naught and 2 pi are constant quantities. I is also a constant quantity in this problem. So mu naught I by 2 pi, these things come out of the integral, and you just have to carry out a very simple integral d phi 0 to 2 pi. So that is what it is. So you just have to make a full loop integration 0 to 2 pi. And so this will give you, the integral will give you 2 pi, this 2 pi and this 2 pi will cancel, and you just have mu naught into I, which is a constant quantity. Now comes something important. B dot dl is equal to mu naught into I. This is mu naught into I. Now I have written something else, mu naught into I enclosed. Let us now try to understand what I mean by enclosed. This is again going back to Gauss. In the Gauss problems, you draw an imaginary Gaussian surface, and that imaginary Gaussian surface will enclose charges. And so it is that here you draw an imaginary Amperian loop. Now the Amperian loop can be outside. This is the cylindrical surface of the wire. This green circle is the cylindrical surface of the wire. The wire material does not extend beyond, let's say it's a copper wire. So here within this green circle, you have a lot of copper, but outside is air or vacuum, whatever. And so this green circle being the circumference of the wire, if your Amperian loop is outside, then it will enclose all the current within the wire. If your Amperian loop coincides with the green circle, this arrow with tracing a black circle over here, coinciding with the green circle. From this point, from this green circle outwards, you are enclosing the entire current in the wire. But suppose your Amperian loop has got a smaller diameter and therefore a smaller circumference, such as this red circle. Then, now you follow this point carefully. Only the current within this red circle need be considered. That is I enclosed. So let's see how many black dots have we got over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 black dots within this red circle. All the black dots outside, they're not really dots, they're straight lines. But you are looking at them down the length, down the barrel, so to speak. And so they appear like black dots to you. So those need not be considered. Just like we have discussed, that if you draw a Gaussian surface, any charge that is outside a Gaussian surface does not make a contribution to the flux. And so it is that any current that is outside an Amperian loop will not make a contribution to the loop integral of the magnetic field, the closed path integral of the magnetic field. So that is what it is. B dot dl is equal to mu naught into I enclosed. So that is an integral form of Ampere's law. Let us now try to see what we mean by that. Okay, here is a comparison with Gauss's law. Gauss's law deals with charges and electric field. Ampere's law, what did Ampere say? Ampere say that magnetic field, Ampere said that magnetic field is the consequence of a current, and that is what you can see. Just like electric field is a consequence of a charge, this Gauss integral form of Gauss's law connects charges with electric field, so it is that Ampere's law in integral form connects current with magnetic field. Both are in the integral form. You just look at it. You have got B here, you have got E here. You have got a loop integral over here, dot dl, path integral over here. And here you've got a surface integral. Basically, the left-hand side over is a closed surface flux. And the left-hand side here is a loop integral. Closed path integral is a loop. Closed path integral here. Now let us look at the right-hand side. Here you have charge enclosed. Here you have got current enclosed. And here you've got 1 upon epsilon naught, and here you've got mu naught. Remember one thing, and this we will come to later, that in electrostatics you will have epsilon naught. If you want to look at its cognate magnetic twin, and I'm using the word twin with emphasis because if you think of a coin, then a coin has got two faces, head and tail. And so it is that electricity and magnetism are two faces of a coin known as electromagnetism. So if one face shows you epsilon naught, the other face will show you 1 upon mu naught, 1 upon mu naught, not mu naught. So if you have epsilon naught in one side, one face, wherever you have a epsilon naught, if you want to look at its magnetic cognate, you just substitute the epsilon naught with 1 upon mu naught. Okay. But then Gauss's law comes with a differential form also. What is the differential form of Gauss's law? It is divergence of E is equal to rho by epsilon naught. So can we then find a differential form of Ampere's law? Yes, indeed we can, just like we use the Gauss divergence theorem to convert this thing to the differential form of Gauss's law. Similarly, we can now use the Stokes theorem to do find something like that. Let us see. So this is, this what we have found over here is Ampere's law in integral form. Now we are going to look at, now we shall look at Ampere's law in differential form. Let us try to see. Here is a wire. I'm just looking at a small cylindrical cross section of that wire, a little cylindrical portion of that wire. So this is the top end of the cylinder. This is the bottom end of the cylinder. This is just like your a can of soft drinks or whatever, Coke, whatever. So this is just like that. The can has been turned over. It is lying on its side. These lines are current lines passing through the cylinder. So if you look at these arrows, these endpoints are the dots that you see here. I have just turned the can a little, a cylinder a little, and now I'm looking at the cylinder from the side. If I look at the cylinder down the length of the cylinder, then I would have just seen something like this, a circle with black dots. Those black dots are the current lines passing straight towards my eyes. So it is with you. Okay. Now, what is the current enclosed within these two circles? I mean, this is a part of a portion of a cylinder. Current lines are passing through the bottom face, entering the cylinder and leaving the top face, like that. So what is the current enclosed within this thing? So if you have to find the current enclosed, you shall have to do a very simple adjustment. You find the cross-sectional current density. What is cross-sectional current density? Current per area. Current per area into the area. Right. So area of this thing times, let's say, area of this circular cross-sectional face times the current flowing through unit area. Current flowing through unit area will have some value. If you multiply by the total area of the cross-sectional face, you will find the total current going through this loop. Okay. So current per unit area, what unit shall it have? What is its dimension or unit in SI system? Ampere per square meter. Ampere per square meter is the unit. I have written something over here, by the way. Current is actually a vector. Although casually we are writing scalar here because we have just taken the scalar magnitude. Right. Current is actually a vector. Current passing through unit area is also a vector, and area element itself is a vector. So if you're just taking the scalar over here, you have to take the dot product of the cross-sectional current density with the area element and then integrate over the full surface area, area of cross-section, that S. Incidentally, I've written something over here. J is equal to rho into V. I shall not get into this discussion immediately, but it will be a very important thing later. What is rho? Rho is charge per volume, charge per unit volume, so charge density, charge per unit volume into velocity, V. V is the speed with the velocity with which the charges are flowing through this cylinder. We will come to this discussion later in detail. If you look at it dimensionally, it is exactly what this thing should be, ampere per square meter. What is the unit of rho? Charge density will be coulomb per cubic meter. And what is the unit of velocity? Meter per second. So coulomb per cubic meter into meter per second. So meter per cubic meter will give you meter squared. So coulomb charge per meter squared per second. But coulomb per second is current, ampere. So coulomb per second we are writing as ampere per square meter. So this is what it is. So, but I'll get into the detailed discussion of this formula later, not now. When we look at Maxwell's correction of Ampere's law, which is not important right now, but I mean, it is important all the time. But as of now, it is not needed. I shouldn't say not important. So anyway, so what we do is that we write the current enclosed within an Amperian loop as the surface integral, as here surface. So surface integral of the cross-sectional current density. Okay. Now, what shall we do next? Here we have got a line integral, and here we have got a surface integral. But there is a way to connect a line integral to a surface integral, and that is through Stokes's theorem. Let us see now. So Stokes's theorem will tell us curl of B dot dA. If this is the line integral, let's not worry about what is on the right-hand side. If this is the line integral, a loop integral, B dot dl, closed perimeter integral, B dot dl, closed loop, then that could be recast into a surface integral by the Stokes theorem, curl of B dot dA, as you have over here. It is written like this. And so this thing is equal to this. That's a mathematical principle, Stokes's theorem. But then this thing is also equal to this. Now, if you compare this, the first formula and the third formula, which are connected to each other through the second formula, the physical discussion tells us B dot dl could be written as mu naught, loop integral of B dot dl could be written as mu naught into the surface integral of J dot dA. Then the mathematical principle of Stokes's theorem tells us that the loop integral B dot dl could be written as curl of B dot dA with the surface integral. So now you'll compare this and this. You've got a dot dA here, you've got a dot dA here, and you've got a surface integral here, surface integral here. So the next thing that you will do is curl of B is equal to mu naught J. So this is Ampere's law in differential form. You can immediately think of Gauss's law in differential form, which is divergence of E is equal to rho by epsilon naught. So divergence of B is equal to, divergence of E as in electric, divergence of E is equal to rho by epsilon naught. So immediately you will see that The divergence has been replaced by a curl. E has been replaced by B on the left-hand side. On the right-hand side, like I told you, if you have epsilon naught, it will be replaced by 1 upon mu naught. So you earlier had 1 upon epsilon naught. Now you've got mu naught. And rho by epsilon naught. Rho is replaced by J, which is the cross-sectional current density. So curl of B is equal to mu naught J. This is Ampere's law in differential form. You can now apply some of your extra mathematical knowledge. You know that the divergence of the curl of a vector field is always zero. Therefore, if you take the divergence of this full expression, then divergence of this thing will be equal to zero. The divergence of the left-hand side will be equal to zero, and so the divergence of mu naught J will also be equal to zero. So mu naught, the constant quantity comes out, and so divergence of J is equal to zero, which is what happens in the case of a steady current. Okay, so basically we have got curl of B is equal to mu naught J. Like I said, Maxwell's equations are simply these. Finding the divergence and the curl of two fields, electric and magnetic field. So we have already gone through the divergence part. Divergence of E is equal to rho by epsilon naught, and divergence of B, the magnetic field, is equal to zero. So now by Ampere's theorem, Ampere's rule, we have been able to find curl of B is equal to mu naught into J. We shall interchangeably use these two formulae, either the integral form or the differential form. It is often that the integral form is easier to use rather than the differential form. So now what we shall do is, just like for the case of Gauss, you applied Gauss's law for various symmetries, spherical, cylindrical, planar, to find what is the charge enclosed and the corresponding electric field. Basically, if you recall your Gauss lessons, there we use this formula E dot dA is equal to charge enclosed by epsilon naught. And then for depending upon various symmetries, for instance, if you were working with spherical symmetry, the the closed surface integral on the left-hand side will give you E into 4 pi r squared, like that, all sorts of things. So here, what we shall do is that we shall do something similar. We shall use Ampere's law in the integral form to find out the magnetic field in certain cases. Let us see. We know that the magnetic field B magnitude part depends on S, but the direction of the magnetic field is along the phi coordinate, unit vector. Okay, and the line element is given by this dss cap sd phi cap plus dzz cap in cylindrical symmetry. Of course, in cylindrical symmetry, it makes sense for us to use cylindrical symmetry, because we already know by now that if you have a wire, because magnetic field arises due to current, and what's the simplest form of a current? Is a current passing through a straight wire. That's the simplest form of a current. Current can pass through all other things also, a copper sheet, a large copper block, all those things will also conduct current. But here the simplest case of a flowing current is through a long one-dimensional wire. Just like the simplest case of a charge is just a point charge, here the simplest case of a current is one straight line current. So if that is what you have, then immediately you will have the application of cylindrical symmetry. Can you please just excuse me for a minute? Sorry. Thank you. I hope all of you are able to hear me. So like I told you, here you have a current flowing through this wire, and the magnetic field will be looping around and around. So the magnetic field, the natural symmetry of the magnetic field due to a long one-dimensional current is cylindrical symmetry. Just like the natural symmetry of a point charge is a sphere, a surface of symmetry of a point charge is a sphere. So what we do now here is that it should be usual for us. And in fact, Ampere's problems are far simpler than Gauss problems. If you have understood the Gauss problems, Ampere problems are much simpler than that. You should have no difficulty here. Let's see how. Here we are in the case of Ampere's law. So we'll take the cylindrical line element because the magnetic field itself is defined by the cylindrical coordinates. And here we write B dot dl. B has got only the phi coordinate of phi cap unit vector, phi component, phi cap unit vector. So phi cap dotted with S and phi cap dotted with Z will be 0. And you'll just be left with phi cap dot phi cap, which is equal to 1. Okay. And so B dot dl will just be Bs into SD phi, this thing. And so when you take that thing, B dot dl will go from 0 to 2 pi, BSS T phi, 0 to 2 pi. And that will be 2 pi S into Bs. B, we don't know yet, but we just surmise that we make an educated conjecture that it will just depend on S. How so? Let's see now. But then Ampere's law tells us that B dot dl is equal to mu naught into I enclosed. And so that is equal to 2 pi S to Bs as we have found. So this loop, closed loop integral gives us this, and Ampere's law gives us this. So basically, we just have to now use this and this. So B vector is equal to mu naught into I enclosed by 2 pi S. And this is the magnitude. Bs is equal to mu naught I enclosed here, as you have. So I enclose, that is what it is. Here should be an E. Okay, so when you have that, so you will use this formula all the time. Just like how do you find the electric field due to distribution of charges in spherical symmetry? We will say that 4 pi r squared into the electric field is equal to charge enclosed by epsilon naught. Therefore, E is equal to charge enclosed divided by 4 pi epsilon naught r squared. So it is here also that what we shall do is to find mu naught into I enclosed divided by 2 pi S. So the basic task all the time, this will be the basic formula that you will use all the time. And the task will be just for you to find what is the current enclosed. As soon as you have the current enclosed, everything else will follow. Let us see. So case 1, you have an infinitely long conducting wire. Okay, very simple thing. We have just discussed this thing, but I'm just going step by step. It's a simple. So here you have a wire. Current is passing through that wire, current I. You have drawn your Amperian loops outside the wire. And since this is the passage of the current, if you use your right hand, if you use the right hand, so if this be the direction of the current, then the curling fingers will point to the direction of both the Amperian loop as well as the magnetic field. And there you are, mu naught into I by 2 pi S. So that is the current enclosed. I enclosed within this loop. How much within this loop? How much current through this loop? How much current is passing? Basically, it is just that. If you have seen circus, you will see a hoop of fire, a circle of fire, and then motorcycle riders drive fast through that circle, or sometimes even big cats, tigers, and lions are made to jump through that circle. So that circle of fire encloses creatures, human beings, and motorcycles or tigers passing through. So these current lines are like that. So that is how it is. So basically, this is a circle through which how much current is passing. So through both the inner circle and outer circle, the same amount of current I is passing, because it's a one-dimensional structure, infinitely long conducting wire. So basically, then you just write this mu naught I by 2 pi S and phi cap. So this is the basic simple formula. Okay, now we'll complicate matters slightly. Here just you have got, in this application, the first application, case 1, was infinitely long conducting wire. Case 2, now follow carefully. Infinitely long solid conductor of radius A. Now let us be a little careful. Here, so earlier when we were talking about a wire, we imagined the wire to be a thin one-dimensional structure. It's just like it doesn't have a cross section nearly. But suppose you are now given a thick copper wire uh, with a cross section, right? In that kind of copper wire, you will see in the overhead cables that carry current in electric transmission lines. So it's not like a very thin wire in your standard household gadget, but rather the thick wires that pass overhead from these electrical towers, the poles. So it's, let's say, some sort of that, something like that. Uh, so here is a cross section of the wire. The total radius of the wire is A, and within that cross section, you have taken a small daughter cross section as indicated by this shaded area, through which current I is passing. So we shall now work on this thing step by step. Since it's a steady current, you basically assume uniform cross-sectional current density. What do I mean by that? That the current is, take any small area on this cross section. I mean, the total anywhere across the circular face. Take any small area. The amount of current flowing per area through that will be the same as any other area of the same size on the cross section. That would not have been true, suppose, if you had more closed lines, current lines here as compared to the outside, in which case the cross-sectional current density will be denser here, larger here in the inner region as compared to the outer region. Huh. Okay. So if the total current is I, and the current is uniformly distributed across the cross-sectional face of this wire, right? So then the cross-sectional current density will be total current I divided by the area of cross-section of the wire, which is pi a squared. What is the area of a disk? Pi into radius of the disk squared. So A is the total area of the full radius of the disk, and so pi a squared is the cross-sectional current density. Now let us see. First case, suppose S is less than A, as in this shaded area. The radius is S, but on the outer periphery, the outer circumference of the wire, S is equal to A. But suppose S is less than A. Sometime, somewhere within the wire, you have drawn your Amperian loop. This is the circumference of the Amperian loop. This circumference contains the shaded area. So the Amperian loop has got a smaller radius compared to the radius of the wire. So S is less than A. Then what is the amount of current enclosed within that shaded area? Let us see. I enclosed will be the cross-sectional current density, which is I by pi a squared, J, that is I by pi a squared into pi. S is the general radius of these daughter Amperian loops, so pi s squared. When this loop coincides with the circumference of the wire, S will be equal to A, and immediately you'll be able to see that the I enclosed will be the total current I passing through the wire. So, but in this case, that is not what you have. So you will just have I S squared by A squared. So B is equal to, what did I tell you? Always B is equal to I enclosed. I'll correct this thing. It's I NC, it is I ENC, I enclosed by 2 pi S. That is what B is all the time. So mu naught into I enclosed by 2 pi S. That is what you work with. Now, what is I enclosed? I enclosed is I into S squared by A squared. Since S is less than A, it will be less, I enclosed will be less than the total current passing through this wire. So B will be equal to mu naught by 2 pi S into I S squared by A squared. And then some cancellation will happen. I'm just doing a little trick over here. This S and this S squared will cancel to give you an S here. And here is an A squared. This A squared, I'm splitting into two parts. Here you have a mu naught I by 2 pi A. And so mu naught I by 2 pi, one A is kept here, another A is kept below the S. Okay, I'm just defining this quantity. Mu naught I by 2 pi A is a constant quantity. So that constant quantity I'm defining by the symbol B naught. So B will be, it's nothing very important. It's just simplification of notation. That is all there is to it. You can leave it like this thing, no problems if you want to. So Bs is equal to B naught into S by A. Now let us see what happens if S is equal to A. If S is equal to A, then meaning S is now an ampere, the radius of an Amperian loop that coincides with the circumference of the wire. Then I enclosed will be the full current I, and so I enclosed will be equal to I, and so B at A will be equal to mu naught I divided by 2 pi A. And that is equal to B naught, as we defined in the previous exercise when S was less than A. So here you have this thing, S less than A, this, and S equal to A, this. You can also find this thing from this formula itself. As soon as you write S is equal to A, this will cancel. S is equal to A by A will become 1, and B at A will be equal to B naught. Okay, now when S is greater than A, so you've drawn your Amperian loop outside the wire. If you have drawn it outside the wire, then I enclosed will be the total current I, but S is no longer, the S no longer has a defined value. S is greater than A, all right, but greater than A, it can have any number, any value. So B will be equal to mu naught into I by 2 pi S, and this is exactly the thing that you see when you work with a B will be equal to mu naught I by 2 pi S. I'm just once again doing the same kind of a little bit of notation jugglery. Mu naught I by 2 pi A into A by S. So mu naught I by 2 pi A is defined as B naught. So B will be equal to B naught into A by S. But before that, I'd like to come back to this formula before I move further. You see, when S is greater than A, B is equal to mu naught I by 2 pi S. But then this formula, mu naught I by 2 pi S, is exactly what you got when you worked with an infinitely long, thin conducting wire, not a solid cross section. So what is the difference? The difference is that here difference and similarity. Difference is that here you have got a thin wire and here you've got a solid conductor with a radius A. So this is so thin that you may assume that it's of zero radius. So outside this, the magnetic field is mu naught I by 2 pi S. Can you please excuse me for a minute? I'm sorry. Sorry, can you please confirm that you can hear me? Hello?
Yes, sir.
Yes,
Uh,
sir.
Sorry, I'm sorry. No, because suddenly in my office there has been a power tripping. But fortunately the computer is working. So anyway, I'm sorry about this constant interruption. So anyway, this is so if you're standing outside a thin wire, for a thin wire, if you're standing outside, it would look like that the magnetic field is mu naught I by 2 pi S phi cap. Okay. But if you have a thick solid conductor of radius A, thick solid conductor, then standing outside the thick solid conductor, you will get the same magnetic field mu naught I by 2 pi S, standing outside. Now, what is happening here? It is that if you are standing outside a thick solid conductor, it will be just the same as the case of standing outside an infinitely long, thin conducting wire. From this point of view, if you're standing outside a solid conductor, it would look like that all the current is just the same as collapsed along the axis of this wire. Just like in the case of Gauss's law, if you're standing outside the Gaussian surface, it would look like that all the current were, all the charges were concentrated at the center. All the charges were concentrated at the center. Here, it would look like that all the current were concentrated at the along the axis of the thin wire of this conductor. So basically, if you're standing outside a thick, solid conducting wire, it doesn't matter. From your point of view, it might just as well be like an infinitely long, thin conducting wire. So that is what it is. Okay, so the next thing that we shall see is that for these three cases, so let's see. This was case number one, infinitely long conducting wire. This is case number two, infinitely long solid conductor of radius A, which is divided into three subparts: radius less than A, radius equal to A, and radius greater than A. Okay, if I were to ask you to plot this, this is how you should plot. B along the vertical axis, S along the horizontal axis. So from within the wire S less than A, from here, B is equal to B naught into S by A. So basically what you will have is that B is proportional to S. You can see this is the equation of a straight line passing through the origin. B naught by A is like a constant. So this is like Y is equal to M into X. So for S less than A, it will be a straight line. Then at S equal to A, it will reach its maximum value, B naught. And then outside, B naught is the magnetic field is B naught into A by S. This thing just inverts itself. Here it is S by A, and now it is A by S. So it is just like a rectangular hyperbola, an inverse behavior, inverse function. So that is what it is. So if you are asked to plot this function, so you should be able to do that. I'm sorry once again. Please just excuse me. Just give me a minute. Just excuse me. Hello? Yes, please confirm you can hear me. Thank you.
Yes, sir.
Okay. Thank you. Okay, so we have discussed case one, infinitely long conducting wire, case two, infinitely long solid conductor of radius A. So the first case was of a thin wire, so thin that you don't have to take its radius to be anything other than 0. So here you have a thick radius, wire of thick radius. Now we shall look at another case, long conducting hollow sheath of radius A, hollow. It's just like a tube, copper tube, let us say. And the current is only confined to the surface of the tube. The inside is hollow, so there can be no current passing through it. So when S is less than A, current enclosed, so S is A is the radius of this hollow tube. So when S is less than A, I enclosed is equal to 0. No current within. If you draw an Amperian loop whose radius is less than the tube, less than that of the tube, I enclosed is equal to 0, and B is equal to 0. I enclosed is 0, B is equal to 0. At S equal to A, I enclosed is I, all of it. So B at S equal to A, here you can assign S a precise value. B at S equal to A is equal to mu naught I by 2 pi A. And so that you define as B naught as you did earlier. And here you have S greater than A, I enclosed is equal to I. So you draw an Amperian loop outside. It's anyway going to conduct the full current once again. So I enclosed is equal to I, and so B will be equal to mu naught I by 2 pi S. S is no longer carrying any defined value, so you just leave it as a general S. So that's the third case. It's quite a simple thing. And the fourth case is just two long conducting hollow sheets of radii A and B. So here you have just had one hollow tube, a copper tube. Here you have two copper tubes. I can expect you to work this thing out by yourself. I'll just briefly touch upon. There's nothing really to work on over here. This is the standard formula. Bs is equal to mu naught I enclosed by 2 pi s. And now you just look at what you have over here. You have got an inner tube whose radius is A, S is equal to A, and the current flowing along that tube is I1. You have an outer tube whose radius is S equal to B, and the current flowing through the outer tube is I2. So when S is less than A, I enclosed is 0, and so B is equal to 0. When S is equal to A, your Amperian loop coincides with the circumference of the inner tube. I enclosed is I1, so B is equal to mu naught I1 by 2 pi A. When S is greater than A but less than B, I enclosed is still I1. You are somewhere between this tube and this tube. Your Amperian loop is drawn somewhere between this tube and this tube. I enclosed is still equal to I1, and so B is equal to mu naught I1 by 2 pi S. Note that you will only write A or B or whatever when S is equal to that value. If S is greater than, less than, all those things, you can't write anything for S. You just write S as S. Right. When S is equal to B, when S is equal to B, I enclosed is equal to I1 plus I2. Okay. And so when you have that thing, B is equal to mu naught I1 plus I2, S is equal to B, your Amperian loop is coinciding with this circumference. I1 plus B is equal to mu naught I1 plus I2 divided by 2 pi B. S is greater than B, I enclosed, so your Amperian loop is now outside. I enclosed is equal to I1 plus I2. Therefore, your magnetic field B is equal to mu naught into I1 plus I2 by 2 pi S. I've just written a question over here. I think you should be able to give its answer. What if currents were flowing oppositely? Let us see. Suppose a current I is going this way and another current I1 is going this way and another current I2 is going this way. So immediately you can see I1 and I2 will tend to cancel each other. And if I1 and I2, oppositely flowing currents, have the same value, but of course flowing in opposite directions, they will cancel each other. It will be I1 minus I1 or whatever you want to call it. And so magnetic field will be 0. So outside, if you draw an Amperian loop through a tube, through enclosing two tubes carrying oppositely directed currents, so then what you will have is a zero magnetic field. This is important because sometimes occasionally, see, you can't avoid getting a magnetic field if you have a current. Just like you cannot avoid getting an electric field if you have a charge, or you cannot avoid having a gravitational field if you have a mass. Right, so you cannot avoid having a magnetic field if you have a current. But occasionally a magnetic field can be a nuisance. You want to cancel the effect of that magnetic field. So just like if you want to cancel the effect of an electric field, suppose a positive charge has created an electric field, how do you cancel the effect of that electric field? You put a negative charge so that they will cancel each other, the other's charges, and it will overall be charge neutral. And so it is that here, if you want to have, if your current is causing a magnetic field, and you want to cancel the effect of that magnetic field, you just have to create another current that is going in the opposite direction, and so they will cancel each other. So that is how it is. So mu naught into I1 plus I2 divided by 2 pi S. So that is what it is. Now let us discuss a few issues. Maxwell's equations. So basically, I mean, see, we have discussed 4 cases, and you can make up as many cases as you want. But these are some basic ideas I have discussed. What are the 4 ideas? Amperian loops are far simpler than Gauss surface problems. And if you have understood all that clearly, then you should have no difficulty understanding all these things. We are just dealing with cylindrical symmetry because current, by its very understanding, must have a linear, I mean, at least should have a linear geometrical structure, a current flowing along a line. And immediately, if you want to create a surface of symmetry about a line, it's a cylindrical surface. So we have just talked about cylindrical symmetry, and we have discussed 4 cases: infinitely long, thin conducting wire, um, infinitely long solid conductor of radius a hollow sheath, and 2 concentric hollow sheaths. There could be other things also. You will be given some tutorial problems to work with these things later. But as I said, I mean, if you have understood the basic principle of what we have discussed, the subsequent tutorial problems can't be a problem, can't be too difficult. Mm. What I shall do now is discuss certain basic principles of Maxwell's equations. But importantly, only for electrostatics and magnetostatics. We still haven't brought dynamics. Right. So be a little careful about that. When I say dynamics, things have to change in time. But there is no appearance of time in these 4 formulae. Let us now see what we have got. Divergence of E is equal to rho by epsilon naught. You know that already. Divergence of B is equal to 0. We have just discussed that. In statics, once again, I'm sorry. Please just excuse me for a minute. Yes, I hope. I hope you're all able to hear me. So in statics, charges are not moving. So if charges are not moving, then the electric field due to static charges will just have some kind of a Coulomb-like dysfunctional property. You can just gather all these static charges within a Gaussian surface and see that the charges will collapse at the center, and it will be like a central force kind of a function f of r, which is what it is. It will have 1 upon r squared kind of a distribution, and as such, the curl of that electric field will be equal to 0. Okay. And just a while ago, we found that the curl of the magnetic field is mu naught into J. This is Ampere's law in differential form. This is Gauss's law in differential form. Now let us first look at these 4. Once again, I stress that these are not the complete Maxwell equations yet. They are just the Maxwell equations for electrostatics and magnetostatics. Okay, if that be so, then let us see. If you look at these 4 formulae, what did I tell you about electromagnetic theory? You just have to work with electromagnetic theory. You just have to work with 2 vector fields, namely the electric field and the magnetic field. Right, electric field as in E, magnetic field as in B. Okay, so the Maxwell equations are simply these: the divergence of the electric and the magnetic field, the curl of the electric and the magnetic field. If you look at these 4 equations, here in the first row you have got divergence, and in the second row you have got curl. In the first column you have the electric field E, and in the second column you have the magnetic field B. Okay, so those are the things about the left-hand sides of these 4 equations. Now what about the right-hand side? You can see that there is a diagonal kind of a symmetric behavior. This has got rho, and this has got rho by epsilon naught. And here on the right-hand side, epsilon naught is replaced by 1 upon mu naught, therefore mu naught goes in the numerator. And rho, charge density, is replaced by cross-sectional current density. So charge will be replaced by current. Charge in electricity will be replaced by current in magnetism. Epsilon naught in electricity will be replaced by 1 upon mu naught in magnetism. And this diagonal will have 0 here and 0 here. So basically what you can see is that rho and J are the sources. If you did not have rho, you wouldn't have electric field. If you did not have J, you wouldn't have magnetic field. Fine. So then there is no such thing But what are these two sources? Rho is charge density, charge per unit volume, and J is cross-sectional current density, current flow per unit area. But what is current itself? Current is simply flow of charges. So basically on the right-hand side, this and this, they contain or convey information only about charges. There is no such thing as a North Pole or a South Pole. I keep stressing this again and again. Be very clear that the reality of nature is that all magnetism all magnetism is due to physical elements of electricity, namely charges. That is what you have. So if you look at these equations, these are the conclusions that you should be able to draw. That electromagnetic phenomena are simply due to charges, rho as in charge density, J as in charge flowing per unit time through unit surface area, cross-sectional surface area. Charge in both cases. I have not mentioned any North Pole or South Pole business over here. Second, magnetic effects arise due to electric phenomena. That's Ampere's law. Ampere stated that, but this is the mathematical expression of Ampere's physical statement. Once again, I would like to remind you that we are not doing mathematics here. We are still doing physics. But the language of physics is mathematics. That is what it is. The thought is physical, the language is mathematical. Just like you can have a thought in many languages, Hindi, Gujarati, English, whatever. In different languages, you convey the same thought. So that is what it is. So this is nature's thought, and it is expressed through the language of mathematics. Okay, and then look, so let us look at this equation. Divergence of B is equal to 0. Magnetic fields have neither a source nor a sink. No monopoles. What do I mean by that? If you had had a positive divergence, if you have a positive divergence, it means that field lines are diverging from a center, a source. If you have a negative divergence, then it would mean that the field lines are converging towards a center, a sink. In the former case, you have the field lines due to a positive charge. In the latter case, you have field lines due to a negative charge. But if you have neither a positive nor a negative divergence, but a zero divergence, then you have neither a source nor a sink. Magnetic fields, as in this equation, divergence of B is equal to 0 is telling you that they have neither a source nor a sink, and therefore no monopoles. What do I mean by that? Let us go back to a diagram we talked about in the last class, and we touched upon today also. Here, if you have this thing, just look at this thing. You break this magnetic. So here's a bar magnet. For convenience only, I've written a North Pole and a South Pole. Convenience and also bowing to convention, but I keep stressing that the reality is that there is no such thing as a North Pole or a South Pole. So if I break this bar magnet, what will happen is that there will be magnetic field lines looping into it, like here. And so as soon as I break this bar magnet, there will be the birth of a South Pole just above the line of breakage, and there will be the birth of a North Pole just below the line of breakage. And instead of getting getting just a North Pole and a South Pole, the two broken pieces will have their own North and South poles. Again, the field lines will start looping and closing upon themselves in the two broken pieces. So unlike in the case of charges, where you can separate a positive and a negative charge, you take a positive charge and it is like in an atom, let's say, you can break the atom apart and you can have its positively charged central nucleus, the ion, and the negatively charged electrons separated from each other. But you can't do the same thing with magnet. You can't separate a North Pole and a South Pole. So if you break a magnet into two parts, each of the two parts will become a magnet unto itself with its own North and South Pole. So that means that you can't break a magnet and say that here in my left hand I'm holding the North Pole of the magnet, and here in my right hand I'm holding the South Pole of the magnet. No, that will not happen. It will not happen because of this formula. Divergence of B is equal to 0. So that is the statement that has been made at the here, or divergence 0, meaning that there will be neither a source nor a sink, and in consequence also there will be no monopoles, no single monopole. A single North Pole or a single South Pole will not happen. Okay, a little bit extra here. Divergence of B is equal to 0, curl of E is equal to 0. Let us look at these two zero equations, here 0 and here 0. What are the consequences of that? If you look at, go back to a vector formula, divergence of the curl of a vector field is equal to 0. So you can equate these two things and you say that B can be written as, the magnetic field B can be written as the curl of another vector field, and this vector field is known as the magnetic vector potential. Whereas here for the electric field in the static scenario, you have curl of E is equal to 0. Curl of E is equal to 0, and then you apply a general mathematical formula that the curl of the gradient of a scalar function is equal to 0. If that be so, then you can equate this and this. Of course, there's a minus sign. We have discussed these things earlier also. So the electric field can be written as the negative gradient of a potential function. And so this potential function psi is known as the scalar potential. So in scalar potential, and in electrostatics, you have a scalar potential. In magnetostatics, you have a vector potential. And then there is finally a comparison between the two. Comparison between electrostatics and magnetostatics. Let us see. Carefully follow this thing. In the case of electrostatics, you have charge enclosed, whatever. In the case of magnetostatics, you have current enclosed, whatever. In the case of electrostatics, you have charge density. In the case of magnetostatics, you have cross-sectional current density. Okay, just a minute. In the case of electrostatics, you have got epsilon naught. In the case of magnetostatics, you have 1 upon mu naught. In the case of electrostatics, you have the electric field, E, and in the case of magnetostatics, you have the magnetic field, B. In the case of electrostatics, you have curl of E is equal to 0. There is complete divergence or convergence, non-zero divergence. And here, in the case of magnetostatics, you have divergence of B is equal to 0. So there is a lot of non-zero curl, but the magnetic field will not diverge from a point and go out to infinity and not come back again. That sort of thing will not happen. So divergence of B will vanish. And then Gauss's law in two forms, in an Ampere's law in two forms. E dot dA is equal to charge enclosed by epsilon naught. B dot dl is mu naught I enclosed. Okay, and then of course this is the integral form and this is the differential form. Divergence of E is equal to rho by epsilon naught and curl of B is equal to mu naught into J. As you can see, divergence is replaced by curl, E is replaced by B, 1 upon epsilon naught is replaced by mu naught, rho, or rather epsilon naught is replaced by 1 upon mu naught, whatever you want, whatever way you'd like, and rho, charge density, is replaced by cross-sectional current density. So basically, as I said, this comparison chart is emphasizing that in the static scenario, well, even in the dynamic scenario also, in both scenarios, electricity and magnetism are two faces of the same coin. They just have the same source. They have the same source, namely charges. So just like I said, that ultimately we have to go back to nature. And in nature, we have to find the physical element of a certain phenomenon. Suppose you have gravitation. You can't have gravitation with zero mass. You need to have physical mass present to create gravitation. And similarly, you can't have electrostatics without charges. And sorry, you can't have electricity without charges. And similarly, you can't have magnetism without its own physical element. What is that physical element? It was thought that the physical element of magnetism was the North Pole, were the North Pole and the South Pole. Physical elements of magnetism were the North Pole and the South Pole. But now, as it turns out, thanks to people like Oersted and Ampere, we realize that nature is not too complex. With a very simple toolkit, she will give us a whole lot of diverse phenomena. And so it is that electricity and magnetism come out of the same physical element, namely charges. except that here the charges can be static, as in rho. Nobody is saying that the charges have to move around for a constant charge to have charge density. But here the charges must move around. You can't have J, which is cross-sectional current density, unless you have a current. And if you can't have a current unless the charges are in motion. So magnetism is the outcome of charges in motion. Okay, so with that, I will end this discussion and I'll just move on to a new presentation. We have 5 minutes. I'll utilize that time. Today we have had some unfortunate disruptions which should not have been happening. But I'll just briefly start on a new discussion. I've stopped the presentation of this slide. I'll just briefly start on a new discussion that will bring us to the dynamics. Please just bear with me. I will start the presentation of that and the little time that we have. Okay, please confirm that you can see this presentation. Can you? Can anybody
Yes,
please?
sir.
Okay, I'll just briefly start on this discussion. So far, we have talked about statics. So far, we have talked about statics. Now, gradually, we shall have to move on to dynamics, because ultimately we are talking about things that are moving around. We can't always say that things are moving steadily all the time. Like if you were a city traffic planner, you can't always hope that all the traffic movement will be very orderly and constant, have a constant volume all the time. It doesn't happen. You know, your experience says that there will be no heavy traffic at uh, 1 a.m. or 2 a.m. in the night, in the morning, very early in the morning, late in the night. But compared to that, there will be a lot of traffic rush at 9 a.m. in the morning or 10 a.m. in the morning. Everybody would be going to work. So things will keep changing in time. So far, all our discussion that we have had was based on uh, static charges and also steady current. Static charges gave rise to electric field, and charges in motion give rise to magnetic field, but we have applied some restrictive conditions on that. We said that the charges are moving all right, but the motion is steady and uniform. It is like, soldiers are marching steadily down our Rajpath so nobody is running faster or slower than anyone else. So as a result, everybody is moving in step, in unison, and you can say that there's a steadiness about it. So now, um, let us gradually bring in dynamics in this thing. In order to do so, we shall first look at, try to understand the concept of electromotive force. And here there's a serious historical anomaly. Electromotive force is not a force at all. How not? We shall discuss that soon enough. For the time being, let us just discuss a current in a loop. Here I've drawn a general current in a loop. Here's a battery, and the battery is causing a current to move around. What does a battery do ultimately? See, you have a wire that is lying, your household wire. Your household wire connection, if this current is, if the switch is turned off, then there is no current flowing through that wire. So as soon as you turn on the switch, or let's not worry about household, let's just consider a simpler system, the laboratory. In a laboratory, you have a current loop, a copper wire. A copper wire that is closed into a loop on itself, no battery or anything. So just a closed copper loop. It does not have any current flowing through it. Only when you place a battery somewhere within that loop and turn on the battery, then we will have the flow of a current. So what basically is a current? Flow of charge. What is causing the charge to flow? A potential difference. Unless you have a potential difference, the charge will not move. Remember, I use, note that I'm using the word difference, potential difference, right? Just once again, I have given this example so many times earlier. Things right at this moment, I believe you are sitting at your desk or wherever, things are all very nicely laid out on your desk, your computer, laptop, your mobile phone, your pen, notebook, everything. So they are not moving around. Why are they not moving around? Because they are all on a flat surface, which is at the same potential everywhere. At the same potential. There's no absence of potential, except that there is no difference of potential from one point to another on your tabletop. If you lift your table at one end, then immediately it will be like a slide. So things will start sliding down from the top end to the higher end to the lower end. So basically, why is that happening? Because in the process of lifting, you have applied some energy to a table and raised one part of the table to a higher potential compared to the other part. And so on the surface where earlier there was zero potential difference, that is to say the potential function was the same everywhere, now one point to another there will be difference of potential. And because of this potential difference, objects will start moving, so they will come from the higher end down to the lower end and maybe even fall off the table. So it is that purpose of a battery is also the same. It just creates a potential difference, and as a result, if the charges in the copper wire will start moving in along that wire. So with a zero potential difference, there will be no motion of charges. Anyway, so in the next class, it's 11:30 already. I will stop now. In the next class, that is on Friday, we will continue with this discussion. This afternoon, we have a tutorial as well. So please be there for the tutorial. I shall send you the link and everything for that. Thank you. I'm sorry about all the interruptions. Today, there was some problem in our office electricity connection. Okay, so hopefully it will be solved by the time the tutorial session starts. Thank you. If you have any question, you may ask me now, otherwise we may leave. Anybody has a question? Nobody? Then you may all please leave. I shall stop the recording.